The history of atomic structure. Today we're going to understand that scientific ideas can develop and change over time as new ideas and technologies reveal new facts and new ways of thinking about topics. Let's have a look at this timeline of the history of atomic structure. So way back in 500 BC, we had alchemists looking to turn one material into another, so copper or lead into gold. We know that can't be done, but a lot of energy was put into that. And it was Democritus in Greece in the 400 BC sort of era who stated that all matter is made up of atoms. So this was very early on, before there were scientific experiments. He said that atoms can't be divided, but that they are very, very small. And he was the one who coined the term indivisible, which is atomos, which is where we get atom from. It was interesting because Aristotle, who was also around in ancient Greece, he was a gatherer of scientific facts. He felt that Democritus was wrong and termed him a quack. And really it's sort of 2,000 years later that Democritus is proved right. So as we move through the timeline here, we actually skip quite a lot of time and we move to the 1700s. We have a guy called Lavoisier in France. He's working out the difference between an element and a compound. We have a chap called Coulomb, also in France, looking at charges. And we're going to focus on this English man called John Dalton. And in 1803, he picks up the atomic theory and starts to develop what we think of as modern atomic theory. And he comes to the conclusion, which is very similar to Democritus, that atoms are indestructible and that the atoms of a particular element are all the same as each other. So here's John Dalton's idea. He referred to it as a billiard ball model. So some billiard ball pictures here. Slight problem with John Dalton's idea. He was saying that atoms of an element are all the same, but he did not really understand about isotopes. So we have some isotopes of hydrogen here, 3 different isotopes, and you can see that in the middle there's a difference going on. So we'll discuss those a little bit more later on. So back to the timeline. We have the development of different equipment going on. So we've got in 1870 someone using cathode ray tubes. They're going to be important for experiments a little bit later. We've got the discovery of X-rays in Germany. And in France there are different scientists like Becquerel and the Curie husband and wife team who are discovering and playing around with radioactivity. And with their discoveries, we have an Englishman called J.J. Thomson in 1898 who has noticed electrons. And he's noticed that electrons are really small. They are smaller than atoms. So now we have the first idea that the atom is the smallest possible thing is being challenged, and these electrons seem to be negatively charged. So J.J. Thomson puts forward the plum pudding model of the atom. Let's have a look at what that would look like. So here is Thomson's plum pudding model, and you can see that what he has are electrons, these negatively charged particles. Because they're tiny, they must have come from the atom, and because atoms are neutral, there must be positive charges somewhere in there to balance out the negative charges. So he has a sea of positiveness in which are dotted negatively charged electrons, and he called this a plum pudding, or it's like a Christmas cake. Sometimes you see it called the chocolate chip cookie model, and these are sorts of images that you can envisage of the plum pudding model. So back on our timeline, Max Planck is in Germany. He's starting to think about the quantum theory. Albert Einstein's doing lots of important things with light waves. We've got a guy called Millikan in the USA in America actually working out exactly how charged an electron is and how little it is. So it finds out that the mass is very small. And we've got Ernest Rutherford, again in England in 1909, doing an experiment with gold foil. And what he does is, I've got a little picture here, he fires radiation in the form of alpha particles at a very thin piece of gold, so gold foil, and he notices that most of the radiation goes straight through. And that tells him that because these particles of radiation go straight through the gold foil, that there must be a lot of empty space in that gold foil. So he realizes that J.J. Thomson's plum pudding model must be incorrect. It can't be a mass, a thick mass of matter which is positively charged, because that would stop his alpha particles going through, and the alpha particles do go straight through. Some do get deflected, and from his results he makes a conclusion that mostly atoms are empty space, but in the center there must be a really dense nucleus and it must be positively charged. So back in the timeline, we will notice that Niels Bohr from Denmark comes up next. And the reason for this is that Rutherford's model, whilst it does explain some aspects of atoms, it doesn't explain everything. And one of the things it couldn't explain is things like chemical reactions, why do they happen the way they do, and things like why metals give off characteristic colours when they're heated in a flame. And that's what Niels Bohr was trying to fix. And so he presented a model with a very dense nucleus, just like Rutherford explained, but the electrons are spinning around the outside in discrete orbits. So his model looks a little bit like this. So we've got discrete levels like steps where you can find the electrons. So his model looks a little bit like a planet in a solar system. So you've got electrons orbiting a central nucleus. And the electrons have a capacity, the electron shells have a capacity, they can hold a certain number of electrons. So you've got 2 in the first energy level or shell or orbit, and then you have 8 in the next one, and 18 in the next one. So you have discrete number of electrons that can appear in each energy level, and you don't get electrons in the gaps in between. And that helped to solve some of the problems that were seen with Rutherford's model. So back in the timeline, we've got Niels Bohr doing his thing in 1913. And we move forward in time to Schrödinger. Schrödinger, working in the 1920s in Austria, he is starting to talk about probability, about the fact that electrons have properties of both particles and waves, and somehow they exist, but it's very complicated to say exactly where they exist. So he's starting to put forward some quite complex ideas of quantum mechanics. So let's have a look at the sorts of pictures he's putting forward. So his quantum model says that electrons have certain energies and you can find them in different places, and he produced diagrams like this where the dark patches show where the electron is most likely to be, but it's not always in that spot. It's just like a probability of where it might occur. But there is still a problem, and the problem at the moment is that when you add up all the negatives and you balance them against the positives so that you have a neutrally charged atom, that doesn't make the right mass. But thankfully in 1931 Chadwick comes along and he discovers the neutron, and a neutron is a neutral particle, does not have a charge, and it makes up the mass that was missing when people were trying to work out the mass of an atom just from the positive and negative charges alone. So hopefully you can see that the understanding of the structure of the atom has morphed and changed and developed and got more sophisticated as our understanding of science has improved, as we have had more equipment to do experiments, and as we have brought ideas from different cultures and different experiments together. So what you'll find is we don't really use the quantum theory. That's very complicated, even at university level. And to explain the kinds of chemical reactions that we will be dealing with at school, we refer back to Bohr's model, a sort of planetary model of the dense nucleus in the middle with the protons and the neutrons, thanks to Chadwick. And whizzing around the outside, we have electrons in specific and discrete energy levels that we can predict, so that we can explain the properties of elements, how they're going to react with each other, and some of the phenomena that we see when we play around with chemicals.